So everybody can see the screen, okay? Yeah, I'm having some problem with my pencil for some reason. I'm unable to solve this issue, so please bear with me if there is any problem. Um, right, so we were counting states, right? So remember what our approach is. So in any axis, first we will go to the K space. Okay, so this is what's happening to my pencil for some reason. I don't know why. This is the x-axis, which is kx. Here will be ky, and here will be kz. And we will be, first of all, solving the Schrodinger's equation, and basically identifying where the allowed states are, right? So remember the distance between them is 2 pi by L and all those, right? So in 3D, you'll have regions like this, multiple regions, and the distance between all points in all three directions will be 2 pi by L. If I do 2D, then what happens? Then there will be one region here, and the next solution for KZ will be somewhere here, very far away from, right? So the distance between this plane and this plane, this will be 2 pi by A, where A is the spacing in the Z direction. So because A is smaller than L, there will be a huge distance between this plane and this plane, right? Now what happens if we go to one-dimensional gate? Then what will happen is that I'll have a system. This will be my system, and electrons can go in the Z direction, but they're trapped in the X and Y directions. And because they're trapped in the X and Y directions, their kx value will be multiples of 2 pi by A. Ky values also will be multiples of 2 pi by A. But kz values will be 2 pi by L. So this is these two are larger than this. And so how will we draw the kx, ky for the one-dimensional case? There the kz values will be like this. It will be like this. This is distance between them will be 2 pi by L. Distance between them will be 2 pi by L. And the so imagine a long wire like this, right? But then the next point here, next allowed states will be here. The distance between these will be 2 pi by A. And the next allowed state will be here, like this. Distance again 2 pi by A, like this, right? So, and the next allowed state is somewhere here, 2 pi by A, right? So next allowed state is here. Allowed states are here like this. So I hope you can now draw these allowed K states, right? Yeah, this distance is also 2 pi by A. So now, when we try to count these K states, what we are trying to do, we basically imagine a function G, capital G. Imagine a function capital G. It's not letting me write at all. I don't know what's happening to my pencil. This capital G, imagine it is basically summing up all the states with zero energy to energy E. So the density of states function that we are interested in density of states that we are interested in is actually the sorry about that. I'm having some problem with my pen. Yeah, so this will be summing the states from 0 to E. All the states with energy 0 to E. Let us imagine this function, right? So if we, the function that we are interested in, g of E, is actually the derivative of this function with respect to E, which is same as the derivative of this function with K into this, right? This is by chain rule. Now, the reason why we do this first is because this is easier to calculate. Okay, why? Because this is this is nothing but counting the states from 0 to all the yeah. So this is basically, this is easier to calculate, right? Because dg by dk is easier to calculate. Remember, all the states from energy 0 to k, this is nothing but 4 by 3 pi r pi k cubed. This is the volume, right? This is capital G of k. So little g of k will be so if I do derivation of 4 by 3 pi k cubed, how do I derive? If I derive this with respect to k, I'll get 4 by 3 pi 3k squared. So 3 cancels. I get 4 pi k squared. This is the d of g by dk. This I'm going to multiply by d of k by d of e. This is another way of doing the derivation that I just showed you, right? So this is how we have been doing the derivation so far for the 3D case. Now for the 2D case, how will we count this? We're going to count the states from 0 to E on this plane. And then we're going to count the states with total energy 0 to E on this plane. And add the two, right? Like that, there is other multiple planes on top also. But now in 2D, the total energy, E total, is nothing but h bar square k squared by 2m k z squared plus h bar square k square by 2m k x squared plus h bar square k y squared by 2m. This is nothing but E of z, right? So this is h bar square by 2m. Remember, this can take any value n pi by a, where n can go from 1, 2, 3, 4, and so on. Okay. So there is a minimum value for this, right? That is E1 basically. What is the next maximum value this can take? 4 times E1. Then 3 squared. So 9 times E1, like that. So the Z component of energy can take value E1, 4E1, 9E1, and so on. But this particular part, just the X and Y part, can actually take the value anywhere from 0 to infinity. Okay. Why is that? That's because the electron is free in the, literally it is free in the X and Y plane, right? Can everybody see the screen? Is screen a problem?
No, sir. Screen is
okay, right? Screen is visible. Okay. Yeah. So 0 to infinity basically, right? So x and y, it can take any from 0 to e. And we have also found this out. What is the density of that particular state? Density of states for that particular thing. So let us write it out now. If we were to plot the density of states as a function of energy, we know that total energy can never be less than E1. Okay, so Z contribution is E1. And so if we count just that, then we're going to plot it like that. We're going to plot it as this. This is the density of states for the small lowest plane, this plane. Okay. Now the next plane has this is going to E1. Next plane will start at 4E1. So if my total energy is, let us say, 5 times E1, there are two ways of doing that, right? I can have energy along Z as E1 and energy along X and Y as 4E1. The XY component, this is Z component. Or I can have energy 4E1 in the Z component and E1 along the Y component. So there is two ways of splitting this. So that is why the moment E becomes 4E1, my density of states will double like that, right? So when we are plotting the full thing, this is how we're going to plot the energy density of states. It's going to look like a staircase function. And the steps of the staircase, this is at 4E1. This is going to happen at 9E1 and so on. E1, 4E1, 9E1 and so on. And here it will be 16E1. And again, it will jump. What is the height of this? That is what we have already calculated in the last class, which is m by 2 h square pi. Okay. So any questions about this derivation? I hope it's clear why we're getting it like this. So the density of states for a 2D system looks like the staircase function. What is the density of states for a 3D system? It starts from 0, but it's going to do something like this, square root of E, right? Proportional to square root of E. Staircase function is going to do something like that. Sorry, it's going to start somewhere here. I'm going to keep on doing something like that, right? So this is the difference between them. Now, what will happen for a now density of states for a 1D system? How we do the for a 1D system is again the same way. The total energy E total is E total can be split into two parts. E of X, three parts. E of Y.
Excuse me, sir.
Yes, yes.
So in the last class, we saw that for 2D, the density of states was independent of the energy.
Yeah, that was when we are counting. See, do you understand this part as to the
Yes,
density
sir.
of states will have multiple planes like this,
Multiple
right?
planes, yes, sir.
So that expression we counted only on this plane.
Okay.
Right. So that's why I told you, when I have total energy, let us say 5E1, I can split it into two ways. So the moment my total energy exceeds 4E1, my density of states will double because I have two ways of splitting that.
Okay.
The moment I go to 9E1, again I have three ways of splitting it. So it will become 3 times. So this, is that clear to you now?
Yes, sir.
Yeah. So in the earlier derivation, we were not taking care of the Z component, right? We eliminated the Z component, only counted the XY component. And that's why we got this. Is that clear?
Yes, sir.
Then we have EX, EY, and EZ. We have EX, EY, and EZ. Here, for a 1D system, this is the free coordinate. Okay, that's how we call it. And my wave function is going to look like this. Phi x, y, z. Wave function is going to look like this. It is going to have a trapped state nx pi by a into x sine of ny pi y by y by a into a into e to the power minus j k z z plus b e to the power plus j k z z. Okay, where nx can go from 1 to 3, ny can go from 1 to 3, and kz can be 2 pi by L into nz, where nz can go 0, plus or minus 1, plus or minus 2, and so on. Okay, so it is confined in the x and y planes now, x and y axis, and it's free in the z axis. In order to count the density of states, imagine the k, how will it look like? It will be like these forest, right? There'll be states like this, and the distance between these will be 2 pi by a, very large. Distance between individual points will be 2 pi by L. So let us first count along this line, and then we'll add the other contributions. So to do that, we basically just look at a one axis only, kz axis, and the points are now like this. First 2 pi by L, this is 4 pi by L, and so on. Each point takes up a distance of 2 pi by L. So per unit length, I have L by 2 pi points. Okay, now we'll do this way. If I have how many capital G, right? How many states are there from 0 to k? How many states are there? Basically, k on this side, k on this side, right? So all the states in between here. So that is going to be 2 times. Total length is 2k. 2k multiplied by L by 2 pi. These many states are going to be there, which is k L by 5 states. But we are not interested in capital G. What we are interested in is this little g, g of e, which is nothing but the derivative of g by derivative of e, which is nothing but derivative of g with k first using the chain rule and derivative of e. So dg by dk is L by pi. dk by de is e is h bar square k squared by 2m. d of e is h bar squared by 2m into 2k dk. So dk by de is 2m by h bar squared into 1 by 2k. So it is 2m by h bar squared into 1 by 2k. K is again can be written as root of 2me by h bar square. So bottom line, what you find out is g of e is going to be proportional to 1 by square root of e. Okay. Now, how does this function look like? If this is x, it's going to be infinite at 0, and then it's going to plateau out like this, right? I'm going to do something like that. It's going to do something like that. Just like 1 by x function only, it's going to look something like that. Now let us consider the total energy, which is the sum of the energy in x plus the energy in y plus the energy in z. The energy in z follows this particular distribution, something that is proportional to 1 by root of e. So what is the minimum this energy for this? It is E1. minimum energy is h bar square by 2m, n pi by n becomes 1, h bar square by 2m, pi by a whole square. So I will call that E1. So the minimum energy possible for the x component is E1. Minimum energy possible for the y component is also E1. And what is the minimum energy for this guy? This guy can take any value from 0 to infinity. What is the next possible value for Ex? It's 4E1. 4E1 is 9E1, 9E1, and so on. Okay. So now what will happen is clearly the total energy can never be less than 2E1. So if I now do the density of states for the total, so this is the energy, this is G of E, it will not start until 2E1. And at that point, it's going to be, I'm going to use another color here. So it's going to look something like that. Okay. And until what is the next possible value of energy? Well, and that is basically like, let us say I have a total energy of 5E1. Let's say 5.5E1. How do I split this? There is only two ways of splitting it. I can split E1 along so minimum energy along X is E1, minimum energy along Y is E1, minimum energy along EZ can be anywhere from 0 to infinity because it's free there. So I will not have any states at all below energy, total energy 2E1. After that, it will follow this inverse thing. But until when, right? So the next possible energy is 5E1. So this is going to be 5E1. And 5E1 I can split in two ways. Either EX can be E1 and EY can be 4E1, or EX can be 4E1 and EY can be just E1. So there are two ways, right? So what will happen the moment I reach 5E1 here, my overall density of states will again double. So it will do something like that. It will jump. And then again, it will come falling down after that, right? So the energy will jump here. Then next, where it will do that, 8E1. 8E1 will have another some specialty. Yeah. So you'll have 3 times degeneracy. So it will start looking something like that. So after I do this procedure, at the end of the day, the density of states for 1D systems look like this. They're going to be 0 until 2E1. Then they're going to do something like that. And we'll do something like that. We'll do something like that, and so on. Where do these discontinuities occur? They occur at 5E1, and the other one will occur at 4E1, 10E1. 10E1 will have something else happening at 8E1. There's something going to happen at 8E1. Something's going to happen at 10E1, and so on. Okay. So how do you really work it out? So you can take some energy between 2 and 4. Let us say 4E1. Okay, this is the total energy, let's say. How do I split it? I have to split it into X, Y, and Z contributions. I can the only one way I can split it. I can split E1, E1, and then 2E1 for Z. This is the only way to split it, right? So I'll have only one degeneracy. And the moment I have, let us say, 5E1, now I can split this in two ways. E1, 4E1, and 0. Or 4E1, E1, and 0. I can split it this way, right? So after 5E1, I'll have two-fold degeneracy. So the density of states will be 2 times. You have to do 2 times basically. So next, I will say, let us say I count 6E1. How do I split this? I can split E1 along X and 4E1 along Y. 4E1 along Y, and then remaining is 1E1, right? So I'll give that to the Z. This is not the only way. I can split it in this way: 4E1, E1, E1. I cannot give anything else to X and Y, right? They can only take value E1, 4E1, 9E1, and so on. So you can see from 5E1 also I have two-fold, 6E1 also I have two-fold degeneracy. Now if I take until I go to say 8E1. 8E1, what is the only way to do it? There's only one way. It's 4E1 here and 4E1 here and 0. That's one way. The other possible way is E1 here, 4E1 here. So 4 plus 1, 5, 3E1 here. That's another way. Or I can have another way, which is 4E1 here, E1 here, and 3E1 here. So notice that the moment I have 8E1 total energy, I have threefold degeneracy. I can split it in 3 different ways. Like that, you can keep on doing it. Okay, so when I go to 10, you will find out that I have 4 ways of doing it, and so on, right? So this is how the density of states will behave for the 1D density of states. Okay, finally we go to 0D, and when we go to
So
0D, yeah,
for 8E1, we can't
yeah,
have more than 3.
how?
I mean, why can't we have 3E1 and then 4E1 and E1?
No, 3E1 नहीं होगा ना. X and Y में E1, 4E1, 9E1 only ऐसा एनर्जी स्प्लिट होता ना.
Okay.
हाँ?
Okay, sir.
See, X and Y are quantum confined,
Yes,
so
sir.
their energy can
Confined.
only go E1, 4E1, 9E1 like that, right?
Yes, sir. And we are independently playing with the Z1.
Only Z we have continuous energies.
Okay.
Okay?
Sir, but like that, even in X and even in Y and 6 even in Z.
That's also possible. Yeah, you're right.
Yes, sir. Yes.
That is possible. Good. Yeah, that's possible. So I can have even here, 6 even here. Yeah. So I guess the degeneracy will become 4 times, not 3 times. Yes. Yes. Okay. So this you have to work it out exactly. So we have a homework problem where you will work it out. I just wanted to show you how it's done. How about 7E1? I mean, and in fact, sorry, even for 6E1 we can do that way, right? E1,
Yes,
E1,
sir. E1 and
4E1. We can do it this way. Yes.
yeah, yes.
Yes. 5E1 here also we can do that. E1, E1, 3E1. We can do that here as well. Yes. So until 4, until here it's 1-fold. Here when we hit, we're going to hit 3-fold. Here we hit, it'll be 4-fold. Yeah. And 10E1, you can again work it out, right? So along X, I can have E1, 4E1, 9E1, and so on. Along Y also I can have possible E1, 4E1, 9E1, and so on. Along Z I can have any value. So along Z I can have any value from 0 to infinity. So I guess from the minimum value possible is 2E1, right? So minimum value possible is 2E1, and the next landmark will be 5E1. Because from 2E1 to 5E1, I can only have one possible way of filling that state. The moment I go to 5E1, then there is actually three ways, because I can do E1, E1 and 3E1, or E1, 4E1 and 0, and 4E1, E1 and 0. Yeah, so the moment I hit 5, I can do this. Then I'm going to hit 4E1. There, as we found out, there is 4 ways of doing it. So like this, you can calculate this. Okay. Any questions about these density of state calculations? So these are very standard. You can find this in any book. Okay. And yeah, any questions? Sorry.
No, sir.
Sir, this thing,
Mhm.
so this is the way of representation, how to feel, like how many way.
Sorry.
What is this thing represent mainly? Like a way of representation of the feeling of the like a carry. What is, I'm not able to
No, man.
understand.
See, let's say the total energy is 7E.
Yeah.
Total energy is 7E1. Right. So we want to find out, let us say at energy 7.E1, how many empty states are there?
Okay.
We're calculating density of states. Now, density of states क्या होता है?
Number of available states.
So how do you calculate number of available states? That is what we are doing here. Okay.
Yes.
Is that clear to you?
Yes, sir. Thank you.
So I'm plotting here. This is the number of available states. Na?
Yes, sir.
I've calculated the number of available states in one dimension, in the case Z dimension, in the continuous dimension. Then I know that, like for example, here, these are the 4 possible ways, right? So this part is already fixed. What is the density of states of value 0? What is the density of value 3E1, 3E1, this 6E1, right? I have to add up all of those to get the, so let us say if you tell me my total energy is 7.E1, finally I'll give you the answer. What is the, how many available states are there at that particular energy? Okay.
Yes, sir.
Hello.
Yes, sir.
Do you understand the density of states concept?
Yes, sir.
So what is confusing here?
No, this is clear, sir.
Okay. Any other question?
No, sir.
Okay. So today there's supposed to be, is there some issue? Why are people not here? Is there some confusion? I don't know.
No, sir. I think there is no confusion from your end. Even I'm thinking the same. Why is anybody not attending the class? I mean, Snehal is having some family issues. He's not in the campus.
He's not there.
currently.
Yeah. I think
Yeah,
who's the other student? I think there is.
Prankush and Aparna. Prankush joined the class, but then he left.
Yeah.
So I don't know. So Prankush was there for like 10
I
minutes.
thought I saw Prankush, and then there was somebody. Aparna is not here today, I guess. Yeah.
Yeah,
Is she
Aparna
also
is
having some problem? I don't know. Yeah. Okay. So that finishes the density of states chapter. So once we finish density of states chapter, now it's time to actually go to crystal structure. So I'm having some problem with my pencil. So what I'm going to do is I'm going to just find this lecture online. So we're going to go through that because of this pencil issue. Yeah. So we're going to do something called the chronic Penne model. Okay. So imagine a crystal, right? If I imagine our crystal lattice, uh, until now we have been ignoring the presence of the nucleus in solving all the quantum mechanics problems. So we've been saying, imagine there is a box, and imagine that the electron is trapped inside this box. Outside the box, the potential is infinite, and inside it is finite, right? Or we are saying, inside it is zero, outside it is some finite value. But we have not really discussed as to what causes that potential. So physically, how would we create such a potential? And now it is time to really look into that, because until now, if I have to summarize what all we have covered, we started with the one-dimensional potential wells, either finite or infinite. Then we did little bit discussion of multiple potential wells, and then we simply took this situation and moved to 2 to 3 dimensions. And when we move to 2 to 3 dimensions, we also were able to write how the wave function looks like in terms of sines and e to the powers, right? And then we also counted the number of states in each kind of quantized system. So we have 3D quantized systems, 2D quantized systems, 1D quantized systems, 0D quantized systems. 3D quantized systems are basically normal materials. There is no quantization. Electron is free to go in all 3 directions. 2D quantized systems are actually quantum wells. These are also called 2-dimensional electron gases and so on, right? So these are quantum wells. 1D quantum systems are actually quantum wires, and 0D systems are actually quantum dots. So we are able to see what happens in each of these cases. For example, in 3D, if I plot my energy level along X, and let us say this is my conduction band, then I'll have, this is the density of states. It's going to look something like that. Instead, imagine that I have this same semiconductor, maybe gallium arsenide. I'm going to pack it into a quantum well. So this is gallium arsenide, let us say, and this is some other material. So if I look at it from this direction, the band structure is going to look something like that, right? Now, what would be the density of states here in this well? This is how it's going to look like. This is the edge of the conduction band. I'll not have any states right at the conduction band because that is E equal to 0, right? So I'll have, everything will start somewhere here, and it will start and it will do something like that. Density of states as a function of energy in a quantum semiconductor quantum well will do something like that. Okay. And you see, for larger values of energy, these two things will almost coincide, 3D and the 2D functions. Now imagine you are able to do a quantum wire made of the same semiconductor. How would the density of states look like for that? Again, there will be nothing in the band gap. We don't worry about the valence band for now. In the conduction band, until 2E1, nothing will happen, right? So I'll have density of states that looks like that. Like this. It will be some jagged arrows, right? Maybe I'll do a slightly better job at this here. So it's going to be 0 until here. I'm going to shoot, then I'm going to go very high. Then after that, it's going to slowly decay like that. Then when it hits 4E1 plus EC, this is EC, right? So this is EC plus 2E1. Then when it hits EC plus 4E1, it's going to again go very high. Then again it's going to drop. And then once it hits some other value, again it's going to go very high. Again it's going to drop. So this is how the density of states is going to look like for a quantum wire. And for a quantum dot, eventually, what will happen? Again, let's say you are using the same semiconductor to manufacture that quantum dot. I'll have simply delta functions. I'll have delta functions like this. So you can imagine this breaking up into steps. Then the steps are going to break up into these kind of peaks, and those sharp are going to break up into delta functions, right? Okay. So now let us think about what would actually happen and in an experiment. How do people measure these kind of things? So what they do is, let us say I have a semiconductor. I'm going to do something called photoluminescence spectrum that will directly give me these kind of plots versus energy. So if you make a quantum well, and if you plotted the density of states versus, you will get a staircase. And if you had a quantum wire, you would get a bunch of arrows like this, right? And if you did a quantum dot, you get very sharp lines like this. Okay. So that is exactly what we have calculated, right? So imagine taking a semiconductor that you know, gallium arsenide, and making it into a quantum well. Then all of a sudden, its density of states is going to start looking like a staircase function, right? Okay. So we have seen this idea, and but here also we have not really imagined how exactly somebody gave you this potential. How did we get quantum confinement in the first place? And for that, what we have to do next is we have to start thinking of nuclei. Okay. And before going to nuclei, let us summarize again from what we have done in the very first class. Imagine our picture of electron was like this. We had a box and we had static nuclei here. And we realized that the electrons were, we thought of them as little ball that is just moving around. You know, this is a wrong picture. Now our picture is slightly different. What we are now looking at is, we take the same box and we now imagine that box as a box, and we imagine now the electrons are actually wave functions that are spread. Each individual electron is actually a wave that is spread throughout that box. Okay, and that is our picture right now. This picture is actually called the Born-Sommerfeld picture. And instead of electrons that are just whizzing around, we now imagine that it is they're just waves, standing waves or propagating waves inside this medium, inside this box, right? And when we take their density of states, and when we do the we run the box quantization and so on, we get what is the Fermi level, what is these things we can get from this also. Okay, so this is the picture that we have. This picture is not complete because yes, you are imagining the electron as a wave. That is very good compared to in your initial picture, which was imagining it as a little ball that is moving around. But we are still have been neglecting the nuclei. So the next question is, what happens to this nuclei? How do we get a more complete picture which considers the electrons as wave functions, and how do we incorporate the effect of these nuclei, right? And to do that is, this is what we're going to do. We're not going to do it in 3 dimensions. Instead, we're going to simplify that picture and go to a 2-dimensional, one-dimensional situation. And let us try to imagine, if I just have one nuclei, the potential energy at the site of the nucleus for an electron would be 0. Okay. And if I potential energy of an electron that is at infinite distance from the nuclei will be infinite. Okay. So the moment you bring it onto the positive core, then you have 0 potential energy. When you start pulling it out, then you need energy, right? So that is why the potential energy for the electron, the farther it is from the nucleus, is higher. Okay. So how does the potential energy function actually look like? It's looking something like this, right? It's looking like a like this kind of a triangular well. So this is triangular well is kind of hard to solve. So let us simplify this. Instead, let us draw something like this. Okay. So this is an abstraction. So this is going to be your minus infinity, and this is going to be 0. And now each atom, each nucleus can be represented like this, right? Each nucleus can be represented like this. And so a crystal, how do we now represent a crystal? If I have a crystal, let's imagine a very simple one-dimensional crystal with the lattice constant A. And now the simplified potential representation of this would be something like this. Something like this, right? So you can say this is 0 here, U0 here, or you can consider the 0 level here, and you can consider this as minus U0, whatever case you can consider, right? So this kind of a potential is somewhat simpler. It's an approximation, obviously. Now in this potential, distance between here and here will be A, right? And this width will be A, this width will be B, this will be A minus B. So B A minus B, B A minus B, like that, right? So this was the potential that these two people, Kronig and Penne, these two scientists, this is the model. They considered the potential to be of this form, and they solved the Schrodinger's equation in that system. Okay, that is somewhat simple, but it is still quite involved. So there is another guy, Dirac, obviously, right? I hope you have heard of Dirac. So Dirac said, we don't even need to consider even this complicated system. Let us consider, let us take this abstraction, and let us, instead of solving for this particular system, let us solve it for a system that looks like this. So he says, just consider a series of delta potentials. This is deltas, okay, and located at a distance of A. And he said, now in this situation, let us solve the Schrodinger's equation, and let us see what are the values of what kind of wave functions we'll get, and what are the eigenvalues in such a scenario. Okay, so this particular problem is actually called the Dirac-Kronig-Penne model, DKP model. And it may not look like the potential for a one-dimensional crystal, right? But it actually has the similar mathematical form, in the sense that it has a periodic potential. And so what Dirac realized is that rather than solving for something that looks very realistic, he said, let us instead solve it in abstract sense. Let us see what the Schrodinger's equation will reveal when we consider a periodic potential. And the simplest of that is a Dirac delta based periodic potential. Okay, and we will actually solve it in this case. And from the solution of this particular somewhat simplified situation, we're going to derive insights about how the electron wave function behaves in a periodic potential, in a general periodic potential. Okay. And that is what we're going to do next. This is where we get the idea of what is mobility, what causes, what gives resistance to electrons, what is the effect of phonons on mobility, what is the meaning of an effective mass. All those ideas actually come when you try to understand how the Schrodinger's equation is solved in a periodic potential, which is what our goal is going to be next. Let me see. So this is, if you want to look up just the chronic penny model, you will find a lot of textbooks on chronic penny model, as you can see here as well. But it's a lot of algebra, right? As I can show you here, let me show you the actual derivation. We're not going to do this, right? So it's a little bit of a very algebraic, lot of algebra is involved here. Okay. And whenever there is a lot of algebra, you tend to lose the physical insight. So I'm not going to solve we can do it, but it's just a lot of work. The same insights can be obtained by the more simpler Dirac chronic, so which is what we're going to look for. Dirac chronic Penny model. And the very first one is the best notes for this. Okay. Yeah, do work it out, and we'll work it out step by step. But I just wanted to show you that this entire notes is very good. This is what I'm going to solve, use for this material. Maybe it will take 1 or 2 more classes to cover this material. Then we're going to keep on sitting down and understanding the physical implications. Once we understand that, then we can go to 2 dimensions and 3 dimensions. You can understand everything about band gaps, semiconductors, effective masses. Everything will become entirely clear. Okay. Until the first few pages, there is no mistake. But when you go to the final page, here there is some mistakes. And for that, he has actually given you comments here. What are the mistakes? So, okay. So anyway, that's just to inform you. So let us think about what is actually being, how we went from a Dirac chronic penny model to a Dirac chronic penny model. Let me show you that first. So imagine our our atom is like this, right? I just showed you that it's a bunch of potentials like this. Now what Dirac did is, he said, okay, let me raise this reasonably high, very high. So then how will it start looking like? It will start looking like that. Something like that. Then he said, let me make this portion a little bit fatter and this portion a little bit narrower. Then how will it look like? Then it will look something like that. Then he said, let me just raise this all the way to infinity. And then that is why we get the Dirac potentials, the periodic potential. Okay, so I hope you see the transition, because many students ask me, "Aisa tha, ye ulta kaise ho gaya?" Right? How did it invert? This is how it happened. Okay. So all the while, this is our 0, this is our U0. So this is our 0, this is almost infinity. Then again, this is our 0, this is almost close to infinity. So now you have 0 here, exactly infinity. This is the transition from Kronig-Penne model to a Dirac-Kronig-Penne model. Okay. And to solve this, we need 2 realizations. First of all, we need to understand how the equation will look like. So for example, I have h square by 2m d square by dx squared of phi plus u of x phi is equal to E of phi. This is the equation that we have to solve, where this u of x is actually a series of delta functions. So u of x is actually equal to u of x plus a. U of x is equal to u of x plus a. And if you substitute that here, if you impose the condition that ux should be equal to u of x plus a, which should be equal to u of x plus n times a, right? It's periodic. So it has a translation invariance if I translate by distance of a. When you do this, and then we look at what are the conditions on phi, right? So we're not going to do this, but there is a very smart mathematician who actually did this. He considered the solution of differential equations when the potential is periodic, right? You might have heard of this guy. His name was Brouin, right? So you might have heard of Brouin zone and so on, right? So this Brouin zone comes because of this mathematician or physicist actually called Brouin. People say Brouillon and so on. It's a French name, so they say Brouin. So this Brouin actually, we are not going to go to the Brouin's his theorem, right? So there is a theorem which, right, and actually what happens is that if the potential is periodic, turns out that your wave function will also be periodic. Okay, not your wave function, sorry, the probability, which is nothing but squared, right? This is also periodic. Obviously, right? Because if I have a potential like this, then because the system is completely translationally invariant, no matter at which point I am, right? Let us say point here or here or here, equidistant from this delta, right? Probability of finding the electron must be same at every location, right? So I can say that phi of x squared is equal to phi of x plus a whole squared. And this implies that phi of x must be, this does not imply that phi of x is equal to phi x plus a. No, right? Because only the mod of it should be periodic, not the wave function itself. And but there is a way to solve this issue. So if my wave function is of the following form. So if the wave function had to satisfy this condition, then we can prove that. And another scientist worked on this. His name was Bloch. Okay, so we have something called the Bloch wave function, right? So Bloch waves. So his name was Bloch. And what Bloch was working on, he said, okay, probability has to be periodic. If probability is periodic, then my wave function should have a very specific form. What is the form of the wave function? The wave function must have a very specific form. It should look something like this. Some function a multiplied by e to the power j capital K x. Okay. E to the power j capital K x plus or minus capital plus or minus capital K x. You are familiar with this. You have already seen this, right? Imagine a plane wave e to the power j kx. So this looks very similar to that, but it is not. Why? There is a difference. The first difference is in a simple plane wave, this a, right? The amplitude does not change with distance. But in a Bloch wave, it actually changes with distance. This is a very important difference between the two. This is called a Bloch wave. This is called a plane wave. And it turns out that your plane wave, this guy will not satisfy the Bloch condition. Does not satisfy. So if I have a periodic potential, your simple plane waves will never satisfy this equation. They are not solutions. They are not eigen solutions of this potential. Okay, why is that? You can check it out. So you can substitute and see that this condition is not sufficient, right? And the most general condition, this is the most general condition, and this will obviously satisfy. Let us prove that it satisfies. How do we prove that? We have to satisfy that phi of x plus a mod of this square must be equal to phi of x squared, right? And let us see that. So a of x plus a into e to the power plus or plus, let's say, j capital K times x plus a mod of this must be equal to mod of a into x e to the power plus j capital K into x. So this implies two things. So we'll work it out. So a squared of x plus a must be equal to a of x, a squared of x, which implies that a itself is a periodic function. And its period is also a. Okay. So in a block wave, phi of x is ax into this a itself is a periodic function. That's the first requirement. Second requirement, sorry, there is no second requirement. This is how we show that a has to be a periodic function, right? So now let's think about it. So we have phi x plus a. This is my wave function is equal to a into x plus a into e to the power j k into x plus a. And we have phi of x, which is a into x into e to the power j kappa into x. So if I divide the two, I can see that phi of x plus a divided by phi of x is equal to a into x plus a by f, but which is 1 because a is periodic, into e to the power j k a. So we also derive the relationship that phi of x plus a is equal to phi of x into e to the power j k times a. This is our second condition. This is a condition that we derive from the Bloch theorem. Bloch theorem says that the solution of Schrodinger's equation, when u of x is a periodic potential, must be of the form a into x, a is a function of x into e to the power plus or minus jkx, where a as a function of x is a periodic function of x with period a. Okay. Any questions about this? Are people following this? Any question? Okay. So wave function has to satisfy this property. Phi of x plus a is equal to phi of x into e to the power j k times a. There is another property of this wave function. I think actually we only need this particular property for now. Notice that we are using this property here. Bloch theorem, right? So this Bloch theorem suggests that phi the book has written the block theorem in this way. And so we can write again this in this way also. Phi of x must be phi of x minus a into e to the power j k a. So these two statements are equivalent, right? So this statement is called the block theorem also. So any wave function that satisfies the Schrodinger's equation in a periodic potential must satisfy this particular thing. So the wave function at x plus a should be equal to wave function at x into e to the power j k a, right? Now you can actually verify, you can do the probability at x plus a and probability at x, and you will see that probability of x plus a is equal to probability at x. So clearly this gives us a periodic probability also. That is why that's how this theorem comes into play. Okay. Now there are some interesting implications of this that we're going to have to examine, which have to do with the fact of what values this k can take and what exactly is this k, right? Remember, until now we have been having the plane waveform e into j into a to the power jk, and we said that this k is nothing but the wavelength, right? Because if I plot this, it's going to look like a simple sine wave. But now I'm telling you another wave function, something that looks very complicated, e to the power j capital K into x. This part looks like a sine wave only, but this part is complicated. It's changing, right? So actually, when you want to visualize this, it actually looks something like this. It is basically a right. So imagine you have an envelope of your sine function that is changing as a function of distance. Okay. So the block wave looks something like this. Plane wave looks something like this. And your block wave looks like the envelope is periodic, right? So remember, you have a AM modulation in electrical engineering. That is exactly what this is. So the block wave is nothing but it's like a AM modulation, and periodic AM modulation of with a sine with a periodic modulation, and the periodicity of that modulation is going to be same as A. Okay, so this is how the block wave actually looks like. So the solution of and why is that? Let me also give you an idea as to why we get something like this. So we have deltas here, right? We have deltas here. So imagine a plane wave that is coming in here. What will happen to that plane wave? Portion of it will get reflected, portion of it will get transmitted. And again, at this wall, some portion will get reflected. This wall, again, portion will get reflected. And like this will happen, right? So there will be multiple waves, infinite, reflections will happen. When all those reflections get added up, your input plane wave, it actually becomes a block wave. So a block wave is actually a result of multiple transmissions, reflections, and they're all interfering with each other. When they do that, you're going to get a block wave. Okay, that is all there is to a block wave. And okay, that is what a block wave. Yes.
Can you repeat last line?
Sorry?
Can you repeat last line?
I don't remember what the last line was.
This one, the Bloch affair, the Bloch wave is reflecting wave.
Right. So if you have multiple, see, imagine multiple see, send a plane wave here, na? Usko kya hoga? Yahan pe they'll have a reflection. There'll be one more transmission here, right?
Yes, sir.
Then this wave is going to hit here and again come back. Like that, there'll be multiple reflections. Are you seeing the multiple reflections?
Yes, sir.
So all these multiple reflections will add together, right? They have to interfere, right?
Yes, sir.
So when they do that, I actually end up with something that looks like this, right? So I end up with something that looks like an amplitude modulated wave.
Okay, like a resultant of the multiple reflection.
Like a what?
Resultant of the multiple reflection.
Exactly, right? Exactly. So that is what a block wave is. It is nothing but it's a resultant of multiple reflections adding each other, and the periodicity of this block is A. Okay, like this, multiple functions are possible, right? So periodicity of that is A. Is that clear?
Yes, sir.
Okay. So yeah, and now it turns out when we do like this, let's say you have a wave function like this, capital K into X. So what exactly is this K? So that K is called the block wave vector. For a simple plane wave, e to the power j I k x, a into e to the power I k x. What is k called? It is called the wave vector, right? So in a similar way, for a block wave, this k is called the block wave vector. Okay, and now I'm going to show you some very interesting property of this block wave vector. Before I do that, notice something. If my wave function is something like this, it's a plane wave, then what is the momentum of my wave function? It is nothing but h bar k, right? That is because the plane wave function is actually an eigenstate of the momentum operator. But it will turn out that this block wave is not an eigenstate. Because it's not an eigenstate, if you give me a block wave vector, block wave wave function, I cannot say that h bar into capital K is the momentum of the electron. It is not. Okay, h bar into K is something called the crystal momentum. It is not the same as a linear momentum. It is something called a crystal momentum. And inside a crystal, anytime we have collisions, your real momentum is not conserved. Only the crystal momentum is the quantity that is actually conserved. So anytime we have in a crystal and so on, right? So we have, remember, we have phonons, all these things, they keep colliding. All those collisions actually don't conserve the linear momentum. They conserve the so-called crystal momentum. Okay. And what is crystal momentum? Adjusting by h bar k. It's not the same as the linear momentum of the electron wave function. Why? Because this block wave is not an eigenstate of the momentum operator. Okay. So I hope I've given you the idea of why the block wave function must be a solution of Schrodinger's equation in a periodic potential. We have some idea about its mathematical form. It's looking like a plane wave, but it is not a plane wave. It's a plane wave. It's an amplitude modulated plane wave. Now there are certain requirements. One requirement is that A is a periodic function of X. A is also a periodic function of X. Okay. Let us check something out now. So I have a wave function psi of x, a into x, e to the power I kx now, my block wave function. And I now specify that AX is a periodic in X with periodicity A. Okay. Now let us do something else. I'm going to consider another wave function, another block wave function. So I'm going to indicate, I'm going to write the index in a somewhat special way. I'm going to write this k na, I'm going to write it as a subscript. So psi kx. So this denotes the block wave with a block wave vector of capital K. Now I'm going to imagine another wave function with a block wave of k plus a. Sorry, not k plus a. K bar. Okay, let's say block wave k bar. K bar of x. So that is going to be a of x e to the power I k bar x. Okay. Now, if both of these are equal, then we can see something. If I have E, I, K, actually I have to specify, sorry, hold on. So I specify that K bar is equal to K plus 2 pi by A. Into N. Why am I doing this? I'm just considering another K bar, which is nothing but K plus 2 pi by A into N, where N can be 0, plus or minus 1, plus or minus 2, and so on. And I'm building another block wave vector with this. Now we're going to compare the two. Okay, that's what we're going to do. So let us substitute for a wave function with K, capital K bar of X. That is going to be A into X e to the power I K plus 2 pi by A into N into X, which is equal to A into X E I K big Kx into E I 2 pi by A into N into X. So here, as you can see, yeah, I think I have just some time left. So if I consider a wave function and I'm simply changing the K value from K to K bar, where K bar is 2 pi by A into N. Okay. And it will now turn out that, so then I'm going to compare it with e k into x, right? This was my original wave function. This was my wave function with a k bar. And if x is equal to a, then this is going to give me 1, right? So if I take k and I change it to k plus 2 pi by a into n, my probability and all the other conditions will actually remain exactly the same. They won't change, right? And I'll have again a periodic function. That is why we say that this k can only, it cannot take all the way, this capital K cannot take all the values from 0 to infinity. It'll actually only take value from 0 to 2 pi by a. And if it takes something larger than 2 pi by a, then what will happen is we get our wave function will get completely reproduced. So I won't have a unique wave function, so to speak, right? And why is that? To show you that, what I want to show here is, consider this function now, what we have done using substituting k plus, right? I can write this as, I can write this in the following way. I can write this as a into x e to the power j 2 pi by a into n into x. I can club this all together, then write e to the power I k x. Okay. Now, what I show you is that this part is anyway periodic with a. Now, this part also is actually periodic with a. Why? Because if I consider this function 2 pi by a n x plus a is equal to e to the power j 2 pi by a n x e to the power j 2 pi by a n into a cancels. So clearly, both of these functions are periodic with a. So I can actually club them together and write like this. The wave function with k bar as a wave vector can be written as a new periodic function multiplied by e to the power j k x. And remember, our old block vector was like this: a into x e to the power j k x. So what will happen is both of these block wave vectors, they may have different modulations, but their crystal momentum is always going to be the same. Okay, so I hope you see this fact that if my wave function has to satisfy something like this, e to the power j capital K into x, if I take a new k, which is this old k plus 2 pi by a into n, then I will once again get another wave function, another block wave function, which may have a different amplitude modulation, but it will have the same crystal momentum. Okay, so that means my crystal momentum, right? My crystal momentum can only go from 0 to h bar into 2 pi by a. This is all it can go. The moment you give me any crystal momentum that is larger than this, I can always express it in terms of something like this, right? So this is why we have the concept of a Boolean zone. Remember, we have first Brillouin zone, second Brillouin zone, all these concepts of Brillouin zones, right? Why does it? Why is that coming into play? It coming into play because this unique mathematical property of a block wave function, that if I have a momentum, if I have a k vector that is equal to k plus 2 pi by a into n, that lies outside the first Brillouin zone, I can reduce it to I can always find an equivalent wave function inside the first Brillouin zone. Okay, so all the unique wave functions, all the unique values of k vector, right? They only lie between in the range from 0 to 2 pi by a. So we can do this in two ways. Either we can do from minus pi by a to pi by a, or we can do 0 to 2 pi by a. Doesn't matter, as long as your total span must be 2 pi by a. So let us say you consider some wave vector that is somewhere here. Then I will say, okay, this is not a unique wave function. It is, its crystal momentum also lies between this band only. Okay, that is why we call this in anything dealing with solution of Schrodinger's equation in crystals or in systems where we have periodic potential, you always see this idea of a Brillouin zone or Brouin zone. And in a one-dimensional crystal, the Brouin zone goes from minus pi by a to plus pi by a. If I have two-dimensional, then my Brouin zone would be a square shaped object in the two dimensions. If it's three dimension, it's going to be a volume around zero in the three-dimension space, right? So yeah, whenever we talk about band diagrams, you see band shapes and so on, it actually comes down to this idea of a Brillouin zone. Any questions about this before I conclude? Okay.